Yo, what's up, everyone? It's your boy here with a special deep dive into the world of machine learning. We're talking about the hottest questions you might face in a machine learning interview. Whether you're a seasoned pro or just starting your journey into AI, this video is your one-stop shop for acing those tough interviews. We're going to break down complex concepts into bite-sized pieces, making sure you not only understand the answers, but can articulate them clearly and confidently. Think of this as your cheat sheet, your secret weapon to navigate the exciting and sometimes intimidating world of machine learning interviews. From supervised learning to neural networks, we're covering it all. So buckle up, hit that subscribe button, and let's unlock the secrets to machine learning interview success. All right, let's kick things off with a fundamental concept. The different types of machine learning. You've got your supervised learning, your unsupervised learning, and then there's the cool kid on the block, reinforcement learning. Supervised learning is like having a teacher in school. You feed the algorithm labeled data, meaning the input and the desired output are already paired up. The algorithm learns to map inputs to outputs based on this training data. Think of it as learning with a set of answers. Unsupervised learning is more like exploring a new city without a map. You give the algorithm unlabeled data, and it has to figure out the patterns and structure on its own. It's all about discovering hidden relationships and insights without explicit guidance. Now, reinforcement learning, that's where things get really interesting. Imagine teaching a dog a new trick. You use rewards and penalties to guide the learning process. The algorithm interacts with an environment, takes actions, and learns from the feedback it receives. Let's talk about finding the right balance in machine learning models. And that's where the bias-variance trade-off comes in. It's like finding the sweet spot between two competing forces. Bias, in simple terms, is how much your model's predictions are off from the actual values. High bias means your model is too simplistic, it's underfitting the data and missing the nuances. Variance, on the other hand, is how sensitive your model is to fluctuations in the training data. High variance means your model is overfitting. It's basically memorizing the training data and won't generalize well to new, unseen data. The goal is to find that sweet spot, that balance between bias and variance. You want a model that's complex enough to capture the patterns in the data, but not so complex that it starts fitting to noise and becomes unreliable. It's all about finding the right level of complexity for your specific problem. All right, let's talk backpropagation. Imagine you're training a deep learning model, right? You want it to learn from its mistakes. Backpropagation is like the model's way of doing just that. It's essentially a feedback mechanism. So you feed your data through the network and you get some initial predictions. These are probably going to be off, especially in the beginning. The model then calculates how much error there is in those predictions. That's the loss function doing its thing. Now here's where things get really cool. Backpropagation takes that error and propagates it back through each layer of the network. Think of it like tracing back the steps of a calculation to see where you went wrong, but on a much grander scale. As the error flows back, the model adjusts the weights, those connections between the neurons, to minimize the error. It's like fine-tuning the knobs and dials of the network until it gets closer and closer to the right answer. It's a continuous process of learning and refining. Backpropagation adjusts the model to reduce errors. How does it make those adjustments? Gradient descent is the optimization engine. Imagine a landscape with hills and valleys. Gradient descent is like a hiker navigating down. The hiker takes small steps in the steepest descent. Each step adjusts the model's parameters. The learning rate controls step size. Finding the right learning rate is crucial. Let's talk about a common pitfall in machine learning: overfitting. It's like when you study way too hard and end up memorizing instead of understanding. The same thing can happen with machine learning models. If a model is too complex, it memorizes the training data. Regularization adds a penalty for complexity. Cross-validation helps check generalization. Let's dive into convolutional neural networks, or CNNs. CNNs help AI process images effectively. They analyze smaller sections of an image, using convolutional layers as filters. These layers detect edges, textures, and patterns. Deeper layers recognize complex features. CNNs learn features automatically. They're powerful for image recognition and self-driving cars. Moving on, let's talk about recurrent neural networks, or RNNs. Now, while CNNs excel at spatial data like images, RNNs are all about sequences. Think about language, for example. Words form sentences, sentences form paragraphs, and so on. RNNs are designed to understand these sequential relationships. Unlike traditional neural networks, they have this unique ability to remember previous inputs thanks to something called a hidden state. It's like having a memory that allows them to understand context. This makes RNNs incredibly powerful for tasks like natural language processing or NLP. Think about machine translation, where the order of words matters a lot, or sentiment analysis, where understanding the sentiment of a sentence requires considering the entire sequence of words. Even things like speech recognition, where you're dealing with a sequence of audio signals, can benefit from RNNs. They can analyze the patterns and dependencies within the audio to accurately transcribe speech into text. Now, let's talk about a crucial concept in machine learning: regularization. You see, when you train a model, you want it to learn the underlying patterns in the data, right? But sometimes models can get a little too enthusiastic and start memorizing the training data instead of generalizing well-to-new, unseen data. This is where regularization comes in. It's like adding a bit of penalty to the model's complexity. Think of it like this. You're trying to fit a curve to a set of data points. Without regularization, the curve might get overly complex, trying to pass through every single point. But with regularization, we're essentially saying, hey, try to find a smoother, simpler curve that still captures the overall trend. This helps prevent the model from getting sidetracked by noise in the data. There are different types of regularization, like L1 and L2 regularization, each with its own way of penalizing complexity. But the main idea is the same: to prevent overfitting and make sure our models can generalize well to new data. Chapter 10, what is the ADAM Optimizer and why is it popular? So, you're training your neural network, right? You've got your data, your model, and you're ready to optimize. That's where optimizers come in. And ADAM is one of the most popular kids on the block. Think of gradient descent like trying to find the lowest point in a valley. ADAM adds finesse with momentum and adaptive learning rates. This makes ADAM super efficient and often faster than other optimizers. For a solid all-around optimizer, ADAM is worth checking out. How do you handle missing data in a dataset? Missing data can be a real headache in machine learning. Some values are just missing. You can't just ignore these gaps. They can mess with your model's accuracy. So what do? You've got options: delete rows with missing values, or use imputation to fill in the blanks. Use the mean, median, or mode. Or try k-nearest neighbors, KNN, imputation. Experiment and see what works best for your data. Don't let missing values get you down. Chapter 12. What is transfer learning? Training a deep learning model from scratch can be a grind. It's like baking a cake from scratch when you could use a pre-made mix. That's where transfer learning comes in. It's the shortcut in the machine learning world. Imagine a model trained on a massive dataset like ImageNet. It recognizes features from edges to complex objects. Use this pre-trained model as a starting point. Fine-tune the later layers for your specific task. It saves time and computational resources and improves performance with limited data. Transfer learning gives your model a head start. All right, so you've got your machine learning models, right? Sometimes one model just doesn't cut it. That's where ensemble methods come in. Think of it like assembling a squad of experts. Bagging and boosting are two popular ways to build these powerful teams of models. Bagging creates a well-rounded team by training multiple models on different data samples. During prediction, it averages their results for robustness. Boosting, however, trains models sequentially, each learning from the previous one's mistakes. This creates a super learner for challenging datasets. We live in a world overflowing with data, often with many features or dimensions. More features, more information, right? Not always. Welcome to the curse of dimensionality. Imagine finding a grain of sand in the Sahara. Too many features make data sparse, complicating pattern recognition. Techniques like PCA help focus on key features. Remember, sometimes less is more. All right, let's talk about autoencoders. These neural networks are like the data compression wizards of the machine learning world. They're all about learning efficient representations of data, kind of like finding the most compact way to store information without losing the important details. Think of it like this. Imagine you have a giant image file and you want to shrink it down to save space. An autoencoder would analyze the image, figure out the underlying patterns and structures, and then create a compressed version that still captures the essence of the original. Now, here's where it gets really interesting. Autoencoders don't just compress data, they also learn to reconstruct it from the compressed representation. It's like they're playing a game of telephone with themselves, passing the information through a bottleneck and trying to preserve as much of the original message as possible. This ability to compress and reconstruct makes autoencoders incredibly useful for a variety of tasks, from image denoising and anomaly detection to feature extraction and even generating new data. They're like the Swiss Army knives of unsupervised learning, always ready to tackle a wide range of challenges. Chapter 16, Cross-Validation, the importance of testing 1, 2, 3. All right, so you've trained your machine learning model. That's where cross-validation comes in. Instead of just splitting your data once, you're doing it multiple times. You're dividing your data into K folds, using different folds for testing and training. It's like giving your model multiple practice exams before the real deal. Cross-validation helps you avoid overfitting. Chapter 17, the learning rate, finding the sweet spot. Let's talk about the learning rate, a crucial hyperparameter in machine learning. It determines how quickly your model learns from the data. The learning rate controls the size of the steps in gradient descent. High learning rates take huge leaps, while low rates take baby steps. Precision versus recall, two sides of the accuracy coin. Accuracy alone doesn't always tell the whole story. That's where precision and recall come in. They give a nuanced view, especially with imbalanced data sets. Imagine detecting credit card fraud. Precision minimizes false positives. Recall minimizes false negatives. High recall means catching actual fraud cases. Chapter 19, the F1 score, precision and recall's balancing act. Sometimes you need a single metric for a balanced view of precision and recall. That's where the F1 score comes in. Think of it like judging a smartphone's camera. You could look at low light and daytime performance separately or use a combined score. The F1 score does that for your model. It's the harmonic mean of precision and recall. More sensitive to extreme values, it reflects low precision or recall accurately, especially useful for imbalanced data sets like credit card fraud detection. It helps find the right balance, crucial for real-world applications. Chapter 20, PCA, dimensionality reduction like a pro. Imagine you're working with a data set that has like 1,000 features. That's a lot of dimensions to visualize and process, right? That's where PCA, or principal component analysis, comes in. It's a dimensionality reduction technique that helps you simplify your data without losing the most important information. PCA finds new axes called principal components that capture the maximum variance in your data. These components are ranked by how much variance they explain. Chapter 21, L1 versus L2, regularization, a tale of two penalties. Overfitting. It's the nemesis of every machine learning model. That's where regularization swoops in to save the day. L1 and L2 regularization are two popular techniques to prevent overfitting. They add a penalty term to the loss function, discouraging complexity. L1, or lasso, encourages sparsity by making some coefficients zero. L2 shrinks coefficients towards zero but not to zero. Choose L1 for few relevant features, L2 for many. All right, so you've got your data and you want to make some predictions. Think of a decision tree like a flowchart for making predictions. It starts with a root node representing the entire data set. Then it splits the data based on the best feature. The tree branches out until it reaches leaf nodes. These leaf nodes represent the final predictions. Decision trees are easy to visualize and understand. So we've talked about decision trees, and they're pretty handy for making predictions. Well, that's where random forests come in. Imagine instead of just one decision tree, you have a whole forest of them. Each tree makes its own prediction, and we combine the results. Think of it like getting opinions from multiple experts. All right, let's talk support vector machines, or SVMs for short. SVMs find the best boundary to separate different classes in your data. Imagine data points on a graph, some circles, some squares, and you want to draw a line that separates them. That line is the hyperplane. SVMs aim to maximize the margin between classes. The margin is the space between the hyperplane and the closest data points, called support vectors. Kernels project data into higher dimensions for better separation. Let's talk about the settings that control how training happens. That's where hyperparameters come in. Think of them like the control knobs on a high-tech espresso machine. You've got your learning rate, which is like adjusting the water flow. Model parameters are the internal workings. Like weights and biases in a neural network, hyperparameters are your external controls. Getting them right can be the difference between a perfect model and an underperforming one. It's all about finding that sweet spot. So you've got your hyperparameters, those control knobs that can make or break your model's performance. But how do you actually find the right settings? It's a bit like trying to perfect a recipe. You experiment, you tweak, you taste test until you find that perfect combination. One popular method is grid search. It's thorough, but computationally expensive. Another approach is random search. Surprisingly, it often finds good solutions faster. Bayesian optimization uses past results to guide its search. Tuning hyperparameters is all about finding that perfect recipe for your model. Well done. You've aced all 25 questions. Any final thoughts before we wrap up?
Machine learning is a never-ending process of learning and adapting. The more data, the better we get.
Couldn't agree more. That's a wrap for today. To all our viewers, keep your algorithms sharp and your data cleaner. Don't forget to like, subscribe, and continue exploring the world of machine learning. Subscribe to Analyst Chronicles for more AI-powered insights and tutorials.